All right, so we've got kind of our standard resistor divider, voltage divider setup, or you could just call them series resistors. There's quite a few names for this specific setup, and we know that our voltage here at this point relative to ground, right? This is our ground point, and that's usually what we hook to our negative of our supply. We usually call that ground or our reference. Um, and so we know that our voltage in the middle here, in between the two resistors, or we'll call it the voltage across R2, is as follows. Right? We've got VR2 equals, and we just got straight, let's actually call this V in. So then we've got V in, and this voltage is being scaled by the ratio of R2 to the entire resistance. So it's kind of like what percentage of the resistance is embodied here, and the bigger resistance has the bigger voltage across it. So that means our equation is R2 over R1 plus R2. So now let's look at two extreme scenarios. So we'll say that R1 is, let's just give it a value like 10,000 ohms or 10 kilo ohms. That's a pretty standard resistor value that you might be able to find in a lab or just around. And now we're going to look at two cases. In this first one, let's look at the case where R2 is 0 ohms. So it's 0 ohms. So that means that really this is just like a wire, right? It's just like a wire that's connected here. And some of you might be able to already intuit what this voltage would become. But if we couldn't, let's see if we can explain it with this equation here. So let's just say Vn is 5 volts. It's a common logic level voltage that we deal with. So we've got 5 volts times, and then R2 is 0. And then we've got R1 is 10,000, so we'll just do 10K plus 0. So essentially we've got 0 over 10. I guess I shouldn't say essentially. It is what we have. And this reduces, or just turns to 0. So 5 times 0 equals 0 volts. So in this case, if our R2 is equal to 0 ohms, meaning that it's a short circuit, the voltage at this point here, right, we're looking at this point here, is 0 volts, right? It's 0 volts. Now let's look at the other extreme here. Let's look at if R2 was infinity ohms, right? A lot of resistance, or essentially saying that there's no resistor here, but there's also no wire. It's an open circuit. Let's see what this voltage, or VR2, would be. Once again, you might be able to intuit what that might be, but let's use our voltage divider equation here. So we've got 5 volts times, and then we've got R2 is infinity, and then R1 is 10K plus infinity. So we've got some infinity over infinity type math going on here. And I'm not going to super get into it because I'm not a math whiz, but I know that this turns to, this kind of just turns into a 1. And so that means that our voltage here is 5 volts. So what that means is, or we can kind of sum this up and say, if we'll make a table of R2 and VR2. So if it is 0 ohms, the voltage there will be 0 volts. If it is infinity ohms, then it's going to be equal to V in. So 0 ohms, we'll just call that a short. And infinity ohms, we'll just call that an open circuit. So the reason why this is important or relevant to digital logic is when we do this, we see that we end up with our standard digital values, right? We have a 0, this is a 0, and we end up with a 1. So these are the two ways that we could adjust to get zeros and ones is by setting this resistance here. And so you might imagine that this is like a potentiometer or a dial that we could change. And if we went from one extreme to the next extreme, we would kind of get this behavior. So it would be nice, and what we're going to look at next, is a component that we can put in place of this resistor that acts as something that we can switch between 0 ohms and infinity ohms.